I'd watch your back, Jimmy. Your Employee of the Month badge isn't so safe anymore. Our prototype glides through aisles, dodges obstacles, and picks up items off shelves like it was made for overtime. No breaks, no pay rises, just pure efficiency. Today, we'll show you how we engineered this reliable, hardworking new hire and why it might just be the future of warehouse work.
Hi, I'm Jasmine and I worked on the mobility subsystem. The goal was to create a system that would move efficiently in a control warehouse, handle inclines, and work in sync with other systems. Tank treads are used with 100-to-1 motors with encoders, allowing use of only 2 motors, saving costs while providing stability and traction. Motor selection was guided by specific requirements, verified through force and speed torque calculation. PID loop is used for precise control. It receives data from the encoders, adjusting speed dynamically, ensuring the robot stays straight. Chassis has routing for organized wiring, reducing interference and increasing accessibility for troubleshooting. Mobility receives input from nav, guiding the robot across the warehouse. In turn, mobility uses functions to align for item collection. 2 custom PCBs were used, one for power distribution and a second for controlling LEDs, allowing the robot to communicate its current tasks with different colors. Power to components, including the Raspberry Pi and the 2 drivers, is handled by a PCB with an XT30 connector and a switch. This improves wiring and ensures reliable power flow.
Good evening, my name is Daniel Rackham and I was in charge of the vision and navigation subsystems. One design consideration we had was with the camera itself. We opted for a third-party camera, the 5-megapixel Ardua cam. This camera was selected since it had high FPS, allowing for decent image processing, a large FOV for increased visibility, and a decent camera quality. We designed our image processing such that the image was converted to a HSV color space and then segmented using InRange. InRange required a lower and upper range for HSV values, providing a greater segmentation range and improving the consistency of the segmentation under varying lighting conditions. Images were further processed using erosion and dilation, which improved the consistency. We used simple contouring and the width outputs to determine distance calculations. Width was used since in many instances the only thing the camera could see was the width of the objects and items. We decided against using homography due to time constraints, but in the future it would definitely help by improving the accuracy of the distance calculations for angled marking. We will now move into the navigation subsystem. Use the state machine to streamline the code approach and simplify functionality. All different actions were split into new states to make code maintainable. This also aided navigation since the camera could be used without being blocked. State machines allowed us to break up navigation functionality into different sections, such as going down rows and returning to packing station. To complete tasks such as going down the row and returning to packing station, we set up mobility functions which could take in bearing from the camera, allowing it to avoid shelves and go down rows without colliding with the shelves. The vision subsystem was designed to aid mobility and navigation tasks with supplying the bearing. The item collection subsystem could be lowered and raised so that the robot could fit into and navigate certain spaces. We chose to design the navigation subsystem this way since the mobility functionality based off object bearing was accurate and acted like a PID controller, leading to smooth navigation. We missed obstacle avoidance and row searching, which will be added in the future.
Hello, I'm Oscar, responsible for the item collection system. I'll present my 3 degrees of freedom robotic arm designed for versatility in warehouse environments. The gripper holds items ranging from 0 to 65mm in width, ensuring a secure grip on various objects. The robotic arm design was chosen for its precision and versatility, allowing more effective retrieval of tricky-to-reach items and fine-tunable camera angle control. This arm collects items from the floor to a height of 34 centimeters, with a maximum forward extension of 30 centimeters for effective drop-off. The robot arm has evolved significantly from milestone 1 to the final product. I added lateral support for the actuators to reduce wear and increase payload. I also shortened the arm lengths for better maneuverability and switched from rubber to polyurethane foam for enhanced grip. This 3 degrees of freedom robotic arm combines functionality and precision, making it ideal for various warehouse tasks.